Dear students, we discussed concept of module in our previous session. Let me recall the definition. Let me recall that we are doing the course rings and modules. For MSc Mathematics at Lahore Leeds University. Let's recall our previous concepts we have already discussed. We defined a left R module to be an abelian group a left R module where R is a ring with identity. A left R module M is an abelian group together with an external law of composition. An external law of composition we also call it scalar multiplication. Scalar multiplication. And we denote it by juxtaposition and is given as R cross M into M such that these are the conditions A plus B multiplied with X multiplied scalar multiplication is equal to AX plus BX. Secondly, A multiplied with X plus Y is equal to AX plus AY. Then number 3, A multiplied with BX is equal to AB multiplied with X. And then number 4, identity element of the ring multiplied externally with X is equal to X. This is for all AB belonging to ring R and XY belonging to abelian group M, which is module. So this is definition of left R module. Similarly, we defined right R module and we proved a proposition that if the ring R is commutative, we also defined right R module and proved that if the ring R is commutative, then every left R module is also right R module. Then every left R module is also right R module, and conversely. That is, every right R module is left R module as well. For this reason, if the ring R is commutative, and of course with identity, please note that during study of modules, every ring we will consider will be a ring with identity. For this reason, if the ring R is commutative with identity, then we shall talk about modules only. If ring R is commutative, then every left R module is right R module as well. Therefore, if the ring R is commutative, we talk about only module. We don't say left module or right module. I give you example that every vector space is a module, and I emphasize that it is not necessary that every module is a vector space. In fact, when we define a vector space, the ring R is a field. Anyway, every vector space is a module, but not necessarily every module is a vector space. Let's have another example. First, we have to recall few concepts. Let's consider this definition. Let G be a group. Then a homomorphism of G into itself. Then a homomorphism then a homomorphism F from G to G, from G into G, is called endomorphism. So a homomorphism of a group into itself is called an endomorphism. And we note that the set of endomorphisms of a group G forms a ring. We note that. Let G be a group. Then the set, let's call it R, then the set R of endomorphisms of G is a ring with identity. Is a ring with identity. Let's discuss it in detail. Let's have small proof for this. So R is F such that F from G into G is group homomorphism. Is group homomorphism. We shall show that R is a ring. So for that purpose, first we have to define addition. We define addition point wise, and you understand that this is what we mean, that is for Fg belonging to R, if we are given two endomorphism F and G, then their sum F plus G is defined as G into G is given by effect of F plus G on any element of G. Let's say that element is X, is equal to Fx plus Fg. Let me remark that the binary operation of group G is addition, where is binary operation in G. And let's take this group G to be an abelian group. So please note that we have taken group G as abelian group and binary operation is addition. So this is the way we define addition on set of endomorphisms of group G. So this is definition of addition. We know that F plus G plus H is equal to F plus G plus H. This is associative law, and it is very simple because associative law holds in group G. So this law is going to hold for ring, not ring, still we have to prove that this is a ring. This law is going to hold in R as well. So associativity holds. Next, 0. In R is given by zero homomorphism, which is 0 maps G into G, defined as zero effected upon X is equal to 0. So that is 0 or additive identity in R. Thirdly, let F belong to R, then we can define minus F from G into G as minus F of X is equal to Fx additive inverse of Fx. What is minus F? What is effect of minus F on X? It is effect of F on X and then negate it. So this is minus F. So that, and you can see that if we add F with minus F, or we add minus F with F, result will be the zero homomorphism. So minus F is additive inverse of homomorphism F in R. So we have seen associativity, we have seen zero element, we have seen additive inverse of each element. Next, we have to see that this addition is commutative. So far we have proved that closure is there, associativity is there, zero element is there, additive inverse is there. So therefore R is group under addition. Finally, we can easily see that F plus G is equal to G plus F for all Fg belonging to R. Reason is because group G is a abelian group, therefore effect of F plus G and effect of G plus F will be same. So F plus G is equal to G plus F, therefore R is abelian group. So we have proved that R, the set of endomorphisms of an abelian group G, is an abelian group. Next we have to define multiplication on R. Now we shall define multiplication for R. Or set of endomorphisms of an abelian group G. We define multiplication for R as composition of homomorphisms. Let me record that. We define multiplication in R by composition of homomorphisms. Composition of homomorphisms. and you understand what composition means. So this is just composition of homomorphisms. That is, for homomorphism or endomorphism belonging to R, we define their multiplication Fg as their composition where effect of Fg on any element of group Gx is given by apply G on X and then apply F on result of Gx. This is for all X belonging to G. So this is the way we define multiplication, and we denote it by juxtaposition. In fact, this is composition of homomorphisms or composition of endomorphisms. Having done that, let's see that conditions for R being a ring are satisfied. First of all, we note that Fg, F composed with G then composed with H is same thing as G composed with H and then composed with F. For all Fg H belonging to R. So multiplication, as we have defined, which is in fact composition of endomorphism, this is associative. Secondly, after associativity, we have to see the distributivity. Further, F composed with G plus H is same thing as F composed with G plus F composed with H, and G plus H composed with F is equal to G composed with F plus H composed with F, and you can see it very easily. This is because F, G and H are endomorphisms. They have same domain and same range. This is for all F, G, H belonging to R. So distributive laws hold. Therefore, R is a ring. We have defined addition pointwise and multiplication as composition of endomorphisms. Finally, we must see that R is ring with identity. For this purpose, to see that R is ring with identity, note that identity homomorphism or identity endomorphism is the identity element with respect to composition in this ring. So to see that R is ring with identity, note that identity homomorphism or identity endomorphism let's denote it by capital I. This is endomorphism from G into G given by effect of I on any element of X is X. So identity endomorphism I is identity element. With respect to multiplication is identity element in R, and therefore reason I write the reason because if we compose any endomorphism with identity endomorphism or identity endomorphism with any endomorphism, results will be equal and will be equal to the endomorphism F, and this is for all F belonging to R. Thus we have proved that R the set of endomorphisms of an abelian group. Remember that abelian group, because a lot depends upon group G being commutative. Thus we have proved that R the set of endomorphisms of an abelian group G is a ring with identity, and identity is the identity endomorphism. We have discussed this example in order to see an example of a module. So let's see example. Of module. This example goes as follows. Let G be an abelian group and R be the ring of endomorphisms of G. Then G is a left R module. Left R module. So let's prove that. In order to prove that, first of all, we note that G is given to be an abelian group. First of all, we note that G is given to be an abelian group. So all we have to do is we have to define an external law of composition or scalar multiplication. So all we have to do is to define the external law of composition and see that the conditions are satisfied. This is very simple. What we define is as follows. We define R cross G, Cartesian product of R and G into G as suppose we are given an element f of R and x of G. Element f of R and x of G. Then note that f is an endomorphism from G into G. So f will act on x because x is the element of G. So f will act on x. So this will be fx and fx will belong to G. Just note that f is endomorphism, a morphism from G into G, and x is element of G. So f will act on x and result will be element of G again. So this is the way we define scalar multiplication. Now let's see that the conditions hold. First condition is if we take two endomorphisms f and g and add these two endomorphisms and apply an element of x, this will be equal to fx plus gx because we have defined addition as pointwise. So this is the first condition. Secondly, suppose we are given an endomorphism F and two elements of group G, X and Y, and we add these two elements. Group G is abelian group and binary operation is addition. So this is equal to Fx plus Fy because F is endomorphism, in particular F is group homomorphism. So this is condition for a group homomorphism. And thirdly, we compose f and g with each other and then apply it on x. And by definition of composition of functions, this is same thing as f gx. So third condition is satisfied as well. And then number 4, if we take identity element, that is identity endomorphism, and apply it on x, result will be equal to x. And this is for all fg belonging to R and xy belonging to G. So all the conditions are satisfied. Therefore, G is left OR module. So this is a very simple example of module. So if we are given an abelian group, then that abelian group is left R module, where R is ring of endomorphisms of the group G. Now let's come to another concept. Let's close it here. So let M be be a left R module, note that M is a abelian group under addition. We use addition for binary operation, then M is a abelian group, and ring R is also a abelian group under addition, and then under multiplication there are other conditions. So module M has 0 element as well. Ring R has 0 element as well. For the time being, we shall denote, we shall write 0 and small r just as subscript. 0R for 0 of ring R and 0M for 0 of module M. So for the time being, otherwise when we are working with the slightly deep concepts, then we don't make these distinctions, but for the time being 0 of module M will be denoted by 0 and subscript M, and 0 of ring R will be denoted by 0 with subscript R. So having done that, let's have a proposition. So let M be a left R module. Then we shall prove that let R be a ring with identity. Every ring is going to be ring with identity, but just to emphasize, to let R be a ring with identity and M be a left R module. M be a left R module. Then we have to prove that 0 of ring R multiplied with any element of module M is equal to 0 of module M, and this is for all x belonging to M. So let's prove that. We know that, and is very simple fact, that when we add 0 with 0 itself, result will be 0. So 0 of ring R plus 0 of ring R is equal to 0 of ring R, and therefore 0 of ring R plus 0 of ring R multiplied with x is equal to 0 of ring R multiplied with x, where x belongs to M. And therefore now you can use that condition for module definition. This is sum of two elements of the ring A plus B, and this is element of the module. So A plus B into x is equal to AX plus BX, and therefore 0 of R multiplied with x and then plus 0 of R multiplied with x is equal to 0 of R multiplied with X. So this is we are using a condition of definition of module here. And also note that when we multiply an element of a ring with an element of module, this element belongs to the module. This element belongs to the module. This element belongs to the module. Now we take this to the right hand side. And therefore 0 of ring R multiplied with X is equal to 0 of ring R multiplied with X minus, we are going to take it on the right hand side, minus 0 of the ring R multiplied with X. And therefore 0 of the ring R multiplied with X is equal to, now note that 0 of the ring R multiplied with X, this is element of module. This is again element of the module. And then when you add an element of a module with its additive inverse, result will be 0 of the module. So this is very important thing to note. This is an element of the module. This is an element of the module. And this element is additive inverse of this element. Element of the module minus element of the module will be equal to 0 of module. Therefore, we have proved that 0 of ring R multiplied with an element of the module is equal to 0 of the module. So, this is proved. We will need this result when we further develop this concept. Let's have another proposition. Let R be a ring with identity and M be a left R module. Let R be a ring with identity and M be a left R module. Then we shall prove that A multiplied with 0 of M is equal to 0 of M, 0 of module for all A belonging to the ring R. So proof is very simple. We know that when we add 0 of module with 0 of module, result will be equal to 0 of module. And therefore, now multiply it with A from the left hand side. Therefore, A into 0 of module plus 0 of module is equal to A into 0 of module. And therefore, use that condition of definition of module, that when we multiply an element of a ring with sum of two elements of the module, then this element of ring gets multiplied with both elements, A multiplied with 0 of the M plus, then they are added, plus A multiplied with 0 of the module. Remember that we are doing this because of conditions of definition of module, and this is equal to A into 0 of module. And therefore A into 0 of module is equal to, you take this on the right hand side, A into 0 of the module minus, it will come as additive inverse on the right hand side, A into 0 of the module. Now this is an element of module. This is an element of module. So element of module added with additive inverse of itself will be equal to 0 of the module. So therefore A into 0 of the module is equal to 0 of the module. So we have proved that if an element of the ring is multiplied with 0 of the module, then result will be equal to 0 of the module. So let's have another proposition. Which says that let R be a ring with identity. Let R be a ring with identity and M be a left R module and M be a left R module, then